A lot of the time, I'm working on developing a mathematical toolbox to deal with electrons that are hot and dense at the same time. Like, you don't have to have role models, but it does change the landscape for you. It changes the possibilities of path that you see in front of you. It just gives you another example.
You just heard from Aurora Pribram-Jones, Assistant Professor of Chemistry and Chemical Biology at the University of California, Merced. Aurora is today's guest on Science in Parallel, a podcast about people and projects in computational science. And I'm your host, Sarah Webb. In this first podcast season, we've been celebrating the 30th anniversary of the Department of Energy Computational Science Graduate Fellowship Program, commonly called CSGF. Aurora was a CSGF recipient from 2011 to 2015 while completing a PhD at the University of California, Irvine. They then did postdoctoral research at the University of California, Berkeley, and at Lawrence Livermore National Laboratory. Join us for a conversation about unusual electron behavior, their non-traditional career path, and the joys of teaching the next generation of scientists. So, Aurora, welcome. This is going to be a lot of fun.
Thank you for having me. I'm excited to be here.
So I actually want to start and learn a bit about what research you're working on right now. What are you excited about?
My research focuses on what electrons do, especially when they're in weird situations, right? So you mentioned I came from some weird situations sort of on my way to academia, and I deal with electrons that are also in, or not bizarre, but different kinds of situations in the way we usually think about them. I'm a theoretical chemist, and most people who do that think about electrons that are in molecules or materials. And I do that too, but a lot of the time I'm working on developing like a mathematical toolbox to deal with electrons that are hot and dense at the same time. So they have thermal effects, like the effects of temperature, but they're dense enough that they still notice their neighbors. And so they still behave quantum mechanically. Other things that we work on are thinking about electrons when you need a little bit more information than you have just in a single low energy state to describe what they're doing. So grabbing information out of the ether that is the excited state and shoving it into the ground state in order to try to get a more accurate description of complicated electronic behavior. So I joke with kids when I go talk at schools and things that my job is to imagine things and draw pictures all day, which is really not very far from the truth. Like, I act like it's me being cute, but it's not. It's pretty much what I do when I'm doing my research. And so we solve a lot of exact models, which are simple problems that we can solve exactly so that we can really dig into them and just put them through the business, right? Like doing all kinds of crazy things to models we know the exact answer for, so that we can then extract that information and try to use it to build useful things for real world situations.
So what are some examples of some real world situations where the things that you do are useful?
So a lot of the work that is funded by the Department of Energy still, because if electrons are hot and dense, they're probably in a few different places, one of a few places. One might be like the centers of giant planets like Jupiter, in fusion experiments, particularly inertial confinement fusion experiments, where you're trying to move from this cool, chilly quantum state and you squeeze things and irradiate them so that then they have to pass through this super complicated region of space that some people call the malfunction junction. It's really hard for us to figure out what's happening there. It's super complicated. And then you get to fusion and yay, fusion's been ignited and you can use more of your plasma physics expertise. So folks who work in that malfunction junction is where I'm probably most useful, because it is really hard and complicated. And so you can also find these things in other like astronomical events or just materials under extreme conditions. So if you slam stuff together really hard, that's another extreme condition that you might find. Where you have really high pressure is another area where some of my work might be interesting. But there are less big sciencey kinds of environments where my stuff might be useful. So you might find something like a system that has ground and excited states. So like the lowest energy state and then the state that's just the next one up. Sometimes with electronic systems, like when we're just talking about molecules, it's a pretty big hop to get up to that first excited state. So you can't really do it at room temperature very easily. But there are some systems where that's a lot lower. Maybe your next excited state, right? You hop up to the next rung of the ladder in energy. maybe it's pretty easy to do that because all you have to do is sort of wiggle your spin a little differently. You might be able to access a bunch of different kinds of states. And when you do that, you might need more information about what's happening outside of the lowest energy state. You might need a little information about what's happening in those quote unquote excited states because they're right there, like they're very accessible. And so in those situations, right, when you might have something that's long and floppy, regular molecule might be interesting, even if it's not in the middle of Jupiter or something like that. So that's another area where having ways of dealing with not just the lowest energy state is useful.
So everything from, what's right around us to the inside of Jupiter.
Yeah, a normal range of applications. Yes. So,
So how did you get interested in this particular area of research?
in undergrad, I transferred from community college to Harvey Mudd College, which is this like tiny, wonderfully weird slash difficult place to be. It's a very small community, really intense. So you can imagine that coming in as somebody who's different was challenging sometimes. Like coming in as a transfer student was sometimes difficult, but it was a really rich experience for me. And while I was there, I got to do undergraduate research. I think I did it for 3 years, where I worked on liquid crystals, and I would synthesize this library of liquid crystals and look at how asymmetry changed how they blended together, how they mixed. So I got to sort of combine the synthetic chemistry with physical chemistry and then do some thermodynamic modeling. So thinking about how to model the energy components that went into how they were mixing. And so when I went to grad school, I wasn't really sure if I wanted to keep doing experimental materials science or move more into the theory part of that work. And I ended up going to UC Irvine because there were a lot of really great theorists there. And in particular, my PI in graduate school, my advisor there, Kieran Burke, set up like a separate interview for me, which let me meet more and more theorists. So when I started talking to him, he works on density functional theory, which is the particular flavor of quantum mechanics that I work on. And I didn't come in thinking I would work on hot electrons, right? That wasn't a plan of any kind necessarily. But when I was starting to apply for graduate fellowships, we connected with Mike Desjardins at Sandia National Labs and Frank Graziani, but in particular Mike Desjardins, who ended up being sort of another mentor for me. And he really helped us start this branch of Kieran's research group that is about thermal density functional theory. And so it was really exciting. I got to sort of meet people who were working on this for the first time and building on work that had happened many decades ago, but was really starting to get play because density functional theory had been used at the national labs with great success in modeling these materials at extreme conditions that they were using in things like the Z machine. And they're like, density functional theory is working really well. Why is that? Isn't that not supposed to happen? Like, don't you need to have temperature in your theory to have it work well? And I was like, oh, that's a good question. Like, why is that working so well? I thought that was a really interesting problem. And the reality is that the CSGF is the reason why this is what I work on so much. We were working on it at that time, but my focus being in this area was really due to me getting funding and getting to focus that way. And then getting to do a practicum at Sandia and connecting with people at Livermore, which is later where I did my postdoc. So all of those kinds of experiences and sort of having the bolstering that happens from like the alumni community and the practicums and things like that at the CSGF really focused my research in this area. So I was excited, right? Like I mentioned, like extreme things are pretty exciting. It's a cool thing to do if you can sort of step outside. I mean, I really do draw pictures on paper, like write equations on paper a lot. So to do work that's on paper, but have it, be able to think about stars or think about planets, right? Getting to think about astronomy for, a weird pseudo material science condensed matter physicist chemist, right? That was a weird and wonderful way to stretch outside of where I was. When you go to the national labs, I mean, big science is really intoxicating in a lot of ways. And so it was neat to be in a community of people who really deeply knew how these materials worked. They had huge insights, both experimentally, computationally, and theoretically, but they were interested in my silly little model systems and like what I saw with these mathematical tools that I was working with. And that was a really fun way to see how my work could impact people working on real systems. which wasn't always as visible in other areas.
Yeah, but that's so cool. Tell me a little bit about density functional theory and what that is.
So, density functional theory is a reformulation of quantum mechanics. So, um, quantum mechanics is this special way of viewing the world, right? We're all quantum mechanical objects and we're all classical objects, but it's this particular perspective on the world. Um, and when you try to solve that problem for, say, you have a bunch of electrons, we use it for electrons a lot because they're lightweight and fast enough that quantum mechanics really matters a lot for them. So if you want to solve chemical or material science problems, you really need quantum mechanics, but it's devilishly hard to solve that for more than one electron at a time. I mean, you can solve it for two. You can get a lot of good answers for a small number of electrons, but for the number of electrons that you have in a molecule or a material, it's impossible to do exactly in practice. And so density functional theory is a way of rewriting that problem so that you don't have to formally solve this coupled differential equation to get something called the wave function, right? Which is describing the state that you're in. And it's this really complicated mathematical object. Density functional theory says, well, what if instead of trying to figure out all these interacting electrons and what they're doing in the system that I care about, what if I instead had a system of non-interacting electrons? So I could deal with each of them separately, but I'm going to put them into a different system that looks different. The landscape they live in is different, but it generates the same density, so the same probabilities of finding those electrons in those places.
You mentioned that your path into science was not the typical road that most people talk about.
That's true.
I guess I wanted to learn a little bit about what were the key steps that got you to science on this non-traditional path of yours.
My mom worked in scientific labs when she was a kid and things like that, but shifted her focus to the rest of the world. Things like being engaged in the community and making sure kids got fed and becoming a teacher and things like that. But it meant that our house was sort of run sort of in between like a mechanical laboratory and a biological laboratory and also a zoo. We had a lot of animals and things like that. My parents made it very clear they had a lot of challenges that became our challenges as well. But one thing that I really treasure from their upbringing of myself and my younger brother is that education and science were not confined to a place or a certain class of people. Our neighborhood kids were encouraged to come in and take all our books and read them and bring them back. And my mom was always asking us to do inquiry, right? Like that was how we were expected to engage with the world and to think carefully. And my family dealt a lot with incarceration, and the stories I heard about that from my dad were often about the books he was reading and things like that. So I grew up in a book home. And my dad was a mechanic, and so there were always engines opened up all over the place and, motorcycles, and you could go in there, and we had a lot of vehicles that were in many pieces and some even that ran. Science was happening all around me, even when I wasn't in school anymore. So I dropped out of high school when I was 15 because things had gotten very difficult at home and the world around us. Part of the fallout from that was that I didn't feel like I could be in school anymore. And I started in community college just because I wanted more flexibility. But I think that there was a period where I didn't think I was allowed to be a scientist in these places, like the places that I am now, because of leaving. And so it took me a while to allow myself to come back to science. And so I had a few different things that I did in the meantime. I was a music major for a while. I played the bassoon and sang and things like that. So I was a music major and did a bunch of other majors and had a lot of different jobs. And one of them was working at a bookstore called Stacy's Bookstore that was a general and technical bookstore. And so once I was in charge, I had keys and I could just sit in there and read at night or study. And so I started testing into science classes at the community college. But I think that was sort of the turning point for me where I realized like, oh, I keep reading all these science books and getting excited and like talking my employees' ears off about it. And they were very good natured about it. But I am differently excited than even people who like science about science. And there's something that's driving me to read math and chemistry books and want to take tests, right? Like that's a weird thing. Who wants that? That's bizarre. But like I wanted to figure out how to do those things, and I really craved that formal education around those things. I really loved chemistry, but when I tested into these classes, I ended up being a triple major in chemistry, biology, and math, and working in tutoring centers there. Like the math center there was mostly staffed by faculty, which was really great. I mean, I went to Foothill College in Los Altos Hills, which is a phenomenal community college. Like California's community colleges are astounding anyway, and it's a particularly strong example of that. And they trained me really well. They trained me really well in science, but they also trained me really well as a tutor and as a peer mentor. And I was a part of programs there that really gave me an identity in science. Like I was a science student, and I don't think that I would have gotten that otherwise. And I had accepted the offer of admission as a transfer student as a biochemist at Berkeley when I got into Harvey Mudd, and I didn't really think that was going to happen. And so I actually sacrificed my deposit there, which was like a huge thing for me at that time of my life. I mean, I was like sleeping on people's floors and stuff a lot of the time, trying to balance all the stuff I was doing.
Wow.
And so, it was like $200 or something, some exorbitant amount of money for me at that time. But I had a feeling that Harvey Mudd would offer me a different kind of opportunity because I was really worried about getting into somebody's lab as a transfer student. So I think a lot of my path was driven by the sort of diversity and depth of experience that I got to have living many lives before I went back to school.
Right.
There are all of these identity formation experiences that happened that I think really cemented for me that I was a scientist. And that was one of them, moving to Harvey Mudd, right? Where even if you're not a scientist, you're a scientist. You're a technical major or minor. That's how it goes. And it's way more about the experience of being in those classes and in those communities than what your major says on your transcript. And then getting the CSGF too. I think a lot of CSGFers have that moment where it's like the deep imposter experience of your first program review when you go and you're like, oh my, I should not be here. Like these people are astounding. And then later realizing that everyone is talking about that the same way, or at least a lot of people are, and realizing that you are part of this group and this community that further solidifies your role as a scientist and gives you a whole lot of pathways to pick from. I'm a deeply awkward person, but I'm strangely comfortable being myself, or uncomfortable not being myself, I guess is more appropriate, a better description of it. But I think that's because of having these like really deep, super strong formation experiences. I worked at a Catholic seminary in the middle of that before times, and so sometimes I talk a lot about formation because that's how you talk about like your calling and your vocation and priesthood and stuff. I'm not Catholic, but I played one for a while. I didn't. They called me heathen baby, and it was a really interesting experience, but I did that for a while. They're a big part of why I got to go back to school, actually, because they were so flexible about my schedule and things.
But what's interesting now to me is that you are now in this role of professor, and
Mm-hmm.
you are now in the role of being that person for students. And I guess I'm interested in what that's like for you now.
It's a huge part of my life. Like I really love my research and being part of this research community and things like that. And I love mentoring my grad students and postdocs too, and my undergrads. But the teaching part of it though, I'm supposed to be in a classroom. It's like I'm good at this stuff, but that's like where I'm supposed to be. Now I get to do that in this exceptional community, right? I love being at UC Merced. It's Our students are astounding. They're brilliant. Most of our students are first generation students. A huge number of them are dealing with things that I dealt with silently, or not so silently as you might imagine, sort of loudly and obnoxiously when I was an undergrad and grad student. And it's really powerful to watch them dealing with these things sort of in real time and to be able to be honest with them about who I am and where I'm from, and that where I'm from is not different now than when I was from there. Like, you don't have to have role models, but it does change the landscape for you. It changes what the possibilities of path that you see in front of you. It just gives you another example. So I really like being able to do that for my students. I get to teach this honors introductory chemistry class, so General Chemistry 1, the honors section, which is a very small class, less than 24 students. And it's their first chemistry class in college, almost all of them. So a lot of the times their first semester, and some of them have never been on a college campus before. And they're talking to me about, how do I talk to my parents about these crazy experiences that are so bizarre compared to what I was dealing with before. And I get to see these students that are meant to be doing science and are doing it despite a lot of messaging that they shouldn't be there.
Your website, I'm going to probably butcher hypogaea, right?
I think that's right.
Is that right? Is that right? The burrowing
right.
owl. I mean, your domain name is hypogaea, and this wonderful image you have of the burrowing owl and the support that you want to give to people who are trying to emerge from the burrow, right? And I mean, I look at a lot of scientists' websites, and it's just something that you don't see all the time, right?
Yeah, I represent a lot of different communities, and it's not always obvious. And so I didn't want people to have to guess, right? Like going back to that thing where I want students to know that if they can see themselves in me, that it's not an illusion. It's where I'm actually authentically from. And there's not a lot of room for that in those recruiting spaces or public. Like, I don't know. I didn't know how to do that. So I actually really struggled with whether or not to put that. There's a certain page on my website that's about this sort of message to students and scientists. And, I've had people reach out to me on Twitter or through Twitter about being gender nonconforming and things like that. People who are not out, but saying like it's really important to me, because I thought about taking it down before too, because people don't always react positively to it, right? But it is distracting to some people because they're not used to people walking in the door with all that being visible. And I was very nervous putting it together. I have like vivid memories trying to figure out how to do this in a way that felt true to me, right? Because I didn't want it to seem, I worry that it seems performative, and I still think about that sometimes. It is a big part of who I am and how I am. So I figured better to let students know right off the bat. I'm probably going to ask about your mental health and your wellness all the time. And I'm probably going to be asking, how have you engaged with your community today, right? Those things are important to me. And I think they're important to your science and your learning. And I think we do a disservice to all of us when we don't allow those tools to flourish, right? They really are cognitive, creative, and analytical tools. And the more we keep people from acknowledging those things about themselves, the more we stunt their growth. And so, yeah, it's my sort of blind and brute attempt to like insert that into the scientific discourse just a little bit. Moving to UC Merced for me is like moving back home in a lot of ways. Not only in the fact that a lot of the students share a lot of the experiences that I had coming into academia, but also it looks kind of like where I grew up. There are, these vernal pools, and there's a lot of marshy areas, and there are these marsh birds all over the, red-winged blackbirds and egrets and stuff all over the place. And that's a very deep part of my upbringing, like going out onto the baylands and things like that outside of East Palo Alto, at the end of our street in East Palo Alto. And that was sort of where I felt safe and at home. And so when I was thinking about coming here, it's like, how do I tell folks that like this is not a new place for me, this is a home place for me? And the owls were a big part of that for me because I remember them there. And also they're super awesome and cute. They're like angsty, cute little birds. I don't know how you wouldn't like them. And they have these really long, spindly legs. If you guys haven't seen them, you should look them up. Or, I guess go to my website, which is weird. But yeah, so it felt sort of gimmicky to name it something, right? So I struggled with this whole thing, but it really did start feeling more and more like myself. And my students have really run with it. So yeah, thank you. Thank you for bringing that up.
Can I ask you a few lightning round questions?
Yeah, let's do it. I sometimes stumble in the lightning round, so I'll try it. Let's do it.
Okay, as a chemist, do you have a favorite element?
Oh, do I have a favorite element? I don't know. I'm pretty into iron. I really like Red Earth, but that sounds dorky. Like, it's not a good one. People are like, really, iron? Iron. That's probably what it is, because I think a lot about plants. Yeah, so I'm obsessed with plants. It doesn't look like that on my website. It looks like I'm obsessed with birds, but I'm obsessed with plants.
Oxidation state? You got a chem nerd for an interview.
That's right. That's right. Oh, I don't know. Maybe 4. It's a weird
nice
thing.
round number.
It is a nice round number. Okay, now I'm going to be thinking about that a lot. What is my favorite oxidation state of iron?
Favorite subatomic particle might be easier, because I think I might have a guess as to that one.
Yeah, it is. I do love electrons. A lot. Like a creepy amount.
And to wrap up,
okay.
I want to ask you, what if you were to pass along one piece of scientific advice or life advice, or something that you would want early career scientists or young scientists, depending on where they are and how they got into science, what would you want to tell them?
I used to say that you should never choose by fear. And I think I stand by that still. Don't make your choices based on fear. I might have an addendum now. It says, like, make sure that they're, girded with kindness, because I think that's hard for a lot of us. But I think they go hand in hand, right? I think if you choose out of fear, you're less likely to be kind. Being kind is bravery. Like, that's a brave thing to do. You can be afraid, just don't choose your path that way. Like, moment to moment or with the big goals. Do the scary thing sometimes. Or maybe all the time.
That seems like a great message to end on. Honestly, I mean, not the easiest, but it seems like the wrap up. So, okay. Aurora, I want to thank you. This was such a pleasure.
Thank you so much for doing this with me. I really enjoyed it. Yeah, anytime you want someone to babble about electrons, let me know. or owls.
I know how to find you.
That's right.
To learn more about Aurora and their work, check out the website hypugaea.com. That's hypugaea.com. You can also find the link in our show notes at scienceinparallel.org. This episode concludes the first season of Science in Parallel, so please check out all 6 episodes. We'll be back in spring 2022, so please subscribe or follow us on Twitter so that you'll be in the loop. Science in Parallel is produced by the Krell Institute and highlights computational science with a particular focus on work by fellows and alumni of the Department of Energy Computational Science Graduate Fellowship Program. Krell administers this program for the U.S. Department of Energy. Our music was written by Steve O'Reilly. This episode was produced and edited by me, Sarah Webb.